All right, purpose for this video is going to be to solve for all the values of a parallel RLC circuit, also known as a tank circuit, because it contains all three components: an R resistor, capacitor, and an inductor. So this question here asks us to determine the total impedance, or Z. I don't know why they put total. To solve for impedance in the given circuit, but just like my other videos, we are going to solve for everything. So I'll start my other ones by stating how is this triangle going to be oriented. So now we're going to get, but now this one's going to be a little more, this is going to be a little bit trickier because we have all three components. We have, again, like I said, the resistor, a capacitor, and an inductor. So in order for us to make that determination, we can do it just by looking at it, and we'll do that as soon as we write our values. And we're going to start this time by writing our values in, our known values. So I have a resistor value. I'm going to scratch them out as I go along. A resistor value of 34 ohms. So my resistor value of 34 ohms. Capacitive reactance XC of 34 ohms. And an XL of 12 ohms. And last but not least, a source voltage of 239. Now we know, obviously, that our 239, I'm just going to write it in now. We know that our source voltage, because voltage is the same in parallel, we can write all those in. So that's what I'm going to go ahead and do real quick. I'm going to write all those voltages in at 239. Now, just by looking at these values, our inductive reactance, capacitive reactance, and resistance, resistance doesn't really factor into this yet to see if it's a capacitive or inductive circuit. If this were a series circuit and we had these values, we would say that this is a capacitive circuit because it has higher ohms, which means it would have a higher voltage drop. But now that it's a parallel circuit, it's going to be the one with the fewer ohms, because the fewer ohms is going to have a higher current flow. So I know by looking at this, it's an inductive circuit because the inductive XL is lower than my XC is, which means I'm going to have higher amps, which means I have more power consumed through my inductor. So let's identify our triangle. We have a voltage is the same in parallel, so voltage is going to be on that parallel line, or on that horizontal line. And then again, Eli and ice. This is ice, ICE, and ELI going clockwise. So again, knowing that it's going to be an inductive circuit because my inductive amps are going to be higher, my triangle is going to be oriented that way. All right, so now getting to the math part of this, the good part. We can answer this question. Honestly, we can answer this question right this very second with a two-step math problem, and we are going to do that, but we're going to do it the same way I've been doing my other videos, parallel. We're going to solve for current, and then solve for total current, and then solve for impedance with voltage divided by current. But in this case here, so we're going to start on the right-hand side again, and I'm going to take my voltage, 239 volts, and divide it by 34 ohms at my resistor, and that's going to give me 7.03 amps. Now, we can also see, common sense and logic, that these are the same values over here at my capacitor, so I'm going to write that my 239 volts and 34 ohms are the same there, so I'm going to have 7.03 amps there as well. Now I'm going to take my 239 volts and divide it by 12 ohms at my inductor, and that's going to give me a value of 19.92 amps. And just like we suspected, our ampacity is higher at my inductor than it was at my capacitor. So now to go over here to my triangle to solve for total current. I've got my resistor value 7.0, or my resistive amps of 7.03 amps goes over here on my horizontal line, just like always. Now, my vertical line, my inductive ampacity and my capacitive ampacity are 180 degrees out of phase from each other, which means it's just going to be bigger number minus smaller number. So I'm going to take my 19.92 amps at my inductor and subtract the 7.03 amps of my capacitive current, and that's going to give me a net ampacity of 12.89 amps. And now that I have my 12.89 amps, I can sit here with Pythagorean theorem and I can solve for my total ampacity in the circuit. So I'm going to take my 12.89 squared plus 7.03 squared, and the square root of that value is going to give me a value of 14.68 amps, which is my 14.68. Now, typically, my total ampacity is going to be the highest. If we just have an RL circuit or an RC circuit or just resistors, we're going to have the total ampacity is going to be the highest value. In the case where we have an inductor and a capacitor in parallel with each other, you can see over here my inductive current is 19.92, but my total current is only 14.68. That is because, and that the math's right, it's just I have circulating current between my inductor and my capacitor. So my inductive current, again, being 180 degrees out of phase with my capacitive current, it does get canceled out with that 7.03. So the math still works. Everything's still fine. Don't panic. All right, so now that I've got my 239 volts divided by my ampacity, my total ampacity of 14.68, I can get an impedance value of 16.28 ohms. Now, if you watch my other two videos, parallel RL or parallel RC circuit, you'll know that we had the product vector sum equation to solve for my impedance if I just had a resistor and either an inductor or a capacitor. In this case, I have both. So the fact that I have both, and again, we can do this a couple of different ways, but the one way we can do it is, well, I'll show you both ways. But the one way we can do it is we can take these two values, right? And we know that our voltage is 239 volts. And we know that our current, right, our net current is that 12.89 amps. And that will give us a total reactance, 239 divided by 12.89. That'll give us a total reactance of 18.54 ohms. And now we can take that 18.54 ohms and we can put it in our product vector sum, right? Because impedance, we'll put it over here, because impedance, Z, is equal to R times X divided by the square root of R squared plus X squared. So I can take that 34 times that X value, 18.54, and divide it by the square root of 34 squared plus 18.54 squared. And that gives me an impedance value of 16.28 ohms. So we could do it that way, or the other way, and we're still going to end up here. But another way that we can get to this value here is called product difference. I can take this 34, the XC34, actually let me write it down first. I can do XC minus XL divided by, XC times XL divided by XC minus XL, quantity of. So I'm going to take the 34 times 12 and divide it by the quantity. So I'm going to use parentheses, 34 minus 12, close parenthesis, and I'm going to get that value of 18.54. Now I can take that and plug it into my Z, the product vector sum. Okay, so I can get this value, the 18.54, either this way or this way, whichever way you so desire to do it. Okay, so now the only couple things we got to do, we got to multiply up to get P, and in class I typically don't do that, but today we will. I'm going to start from the right side of my resistor, 239 times 7.03. I get 1680.17. 1680.17, and that's 1680.17 because the values are the same, times 19.92 gives me 4760.88, and times 14.68 gives me a value of 3508.52. Now, if you are a fan of solving for power factor by using true power over apparent power, we can do that. We don't need to do any additional steps. But if you want to use your power triangle to check your answers, you have to keep in mind that your inductive power and your capacitive power are 180 degrees out of phase from each other. So you would have to subtract the 4760.88 minus 1680.17, and that would be your vertical component for your power triangle. But we can solve for power factor, again, just like we have been for everything in parallel. We can solve for power factor by either doing the true power, 1680.17 divided by 3508.52, or we could do Z over R, 16.28 divided by 34. Or, like I've been doing the whole time, I'm going to do IR 7.03, which is over here. I'll change the color to multicolor. Maybe. There we go. My resistive current of 7.03 divided by my total current of 14.68. And when I do that, I get a power factor, still writing in multicolor, power factor of 47.89%. And now my phase angle is going to be the inverse cosine of that value, which is 61.39 degrees. And that should cover everything. We solve for everything. Again, they said solve for impedance. We could have just done that, again, fairly early by either doing the product difference, product vector sum method and getting the 16.28, or once we solve for our total current, taking our source voltage divided by total current. So to answer the question,